In this video, I'll overview the use of polynomials for the analysis of optimization algorithms, which is a topic that has seen a recent resurgence in the theoretical machine learning research area. This video was inspired by a series of blog posts by Dr. Fabian Pedregosa, and I would encourage anybody who's interested in extra details in the topics to follow the link in the description to this video to each of these blog posts. Before diving into the main content of this video, I want to give some general background on polynomials. So polynomials have been long applied to problems like solving linear equations or equivalently minimizing quadratic objectives. And this led to the development of algorithms like the Chebyshev iterative method or the conjugate gradient method. Additionally, polynomials tend to have many well-known properties that are useful for analysis, and especially well understood are a special kind of polynomial called Chebyshev polynomials, which we'll denote as CPs throughout the rest of this video. So our general goal is to take an optimization algorithm and associate it with a polynomial. Then we can leverage known properties of this polynomial to study the behavior of this optimization algorithm and derive things like convergence rates based on the analysis of the associated polynomial. And as mentioned previously, such polynomial analysis has seen a huge resurgence in recent theoretical machine learning research in areas like PCA, decentralized optimization algorithms, or even the analysis of quadratic objectives. What are Chebyshev polynomials? Well, Chebyshev polynomials are just groups or sequences of polynomial functions that are related to the sine and cosine functions. They're most commonly defined either recursively or with respect to trigonometric functions, and they're widely used within approximation theory. Most commonly, you'll encounter Chebyshev polynomials of either the first or second kind, but there's also the third kind, fourth kind, and so forth. At the bottom of this slide, I provide both the trigonometric and recursive definition of Chebyshev polynomials of the first and second kind. And one interesting thing that you may notice is that the recursive definition of these polynomials is very similar. In fact, they only differ with respect to the first order term, where we have either x for the first kind or 2x for the second kind. Chebyshev polynomials are most commonly analyzed in the domain of -1 to 1, and the behavior of first and second kind Chebyshev polynomials within this domain can be observed in this image here. One difference that you'll notice between these polynomials is that Chebyshev polynomials of the first kind achieve extreme values of plus or minus 1, while Chebyshev polynomials of the second kind achieve extreme values of plus or minus n plus 1, where n is the degree of the polynomial. However, there are many similarities in the behavior of these two kinds of Chebyshev polynomials that you can see in this image. First of all, both kinds of Chebyshev polynomials achieve extrema within the endpoints of the domain -1 to 1. Additionally, they achieve the same number of extrema within this domain that are at alternatingly positive and negative positions, which implies that the same number of zeros occur, exactly n of them, within the domain -1 to 1. Another interesting property of Chebyshev polynomials is the fact that they're orthogonal. And what this means is that if you take the orthogonality condition shown here and the weighting function shown here, this orthogonality condition holds for all Chebyshev polynomials. Additionally, Chebyshev polynomials of the second kind can be defined with respect to Chebyshev polynomials of the first kind as shown here through this integral. Now that we have some general motivation for using polynomials to analyze optimization algorithms, we can consider the objective that we'll be looking at in this video, which is given by this strongly convex quadratic objective here. Interestingly, this objective is very conducive to analysis with polynomials because its form generally gives rise to some polynomial form. And interestingly, extending analysis with polynomials from such a quadratic objective to more general objectives is an open research problem and in often cases is very difficult. Within this objective, H is a positive definite square matrix, and we aim to minimize the objective with respect to X, and we'll denote the unique optimal solution as X star. And we define the largest and smallest eigenvalues of H as big L and little l respectively. To solve such an objective, we generally use gradient-based methods, where iterates are a weighted combination of previous iterates and past gradients. And generally, the main idea here is that any gradient-based method for solving this objective can be matched with a polynomial function that determines how fast it's going to converge. To begin better understanding how polynomials can be used to analyze this objective function of interest, we will start with the illustrative example of gradient descent. And gradient descent is given by the recursion here. This is the canonical way of writing gradient descent for strongly convex functions. If you've seen it before, maybe you're a bit confused because in the denominator here, we usually have the Lipschitz constant plus the strongly convex constant. So it's nice to notice that big L and little l, or the largest and smallest eigenvectors of our H objective matrix, actually correspond to the Lipschitz constant and the strongly convex constant. So if we begin at this recursion, and then we notice that the gradient of our objective at the optimal point x star is 0 and subtract x star from both sides, we can massage this expression to arrive at something that looks like this. And what we have here is that on one side we have our t plus 1 iteration minus x star. On the other side we have our initial point minus x star multiplied by some expression here. And if we look at this expression, what it is it's a matrix multiplied by itself t plus 1 times. In other words, it's a matrix polynomial of order t plus 1. So, from our original expression for gradient descent, we've now arrived at another expression that is expressed with respect to some matrix polynomial. So, if we take this expression and take norms on both sides, invoke Cauchy-Schwarz, and use some nice properties of the operator 2 norm for symmetric matrices, we can arrive at this expression here. And what we can see is that the error of our algorithm at the t plus 1 iteration is less than or equal to, it's upper bounded by the error at initialization multiplied by some polynomial. So, if we want to find the convergence rate for this algorithm, all we have to do is analyze this polynomial and find what is the worst case value of this polynomial. So if we do this, we arrive at the expression here where we get the canonical big L minus little l over big L plus little l convergence rate for gradient descent. Now that we understand the analysis of gradient descent with polynomials, we can move on to more general gradient-based methods given by the recursion here. Here, each iterate is given as a linear combination of the current iterate, current gradient, and the difference of previous iterates. And it's important to note that the coefficients here are scalar valued. Although this expression might look a bit complicated, it can recover familiar algorithms such as Polyak momentum. But because the coefficients are scalars, it can't recover anything with a matrix preconditioner such as BFGS or Atom. So in order to analyze this gradient-based optimization algorithm, we need to associate a polynomial with it. And in this case, that's given by the polynomial shown here, which we will call the residual polynomial. To derive this residual polynomial, we can do a proof by induction. I won't go over that in this video, but if you're interested in that, you can go to the description of the video and read the first blog post of the series of blog posts that I mentioned at the beginning of this video. But given this residual polynomial that we associate with our optimization algorithm, there are some interesting things that we can notice. First of all, the 0th order polynomial is always equal to 1. And this must be true in order for the base case of our induction to hold, which is interesting. Additionally, it's always the case for any residual polynomial that for the tth order polynomial, if it's evaluated at 0, it must be equal to 1. So this property must always be true for any residual polynomial, and this becomes quite relevant to later analysis of our gradient-based optimization methods with this residual polynomial. Given this residual polynomial, though, we can also show something even more interesting, and that is the equivalency shown here. Namely, that our residual at iteration t is a product of two things, the initialization and our residual polynomial evaluated at our objective matrix H. So here, the current error depends on only two things, the polynomial and the initialization. And further, if we take the eigen decomposition of H and leverage some special properties of the operator norm, we can express this as a scalar polynomial instead of a matrix polynomial shown here. And we get our final convergence rate associated with this residual polynomial. And the interesting thing here is that our residual at time t is upper bounded by terms that can be nicely coupled and interpreted. So here, one of the terms in our upper bound is the initialization. It's our initial point minus our optimal point x star. One of them is just our polynomial, and this polynomial is evaluated over a range given by the eigenspectrum of our objective matrix. So what we see here is that the convergence rate of our general gradient-based method is separated into two components. One of them is the initialization, and one of them is based on the analysis of the polynomial. And the maximum value of this polynomial will again give us our convergence rate. So we can see that the analysis of our algorithm is nicely separated from the initialization to where it's completely captured within the behavior of this polynomial. In the previous slide, we developed a general gradient-based optimization methodology. Then we associated a residual polynomial with this methodology and solved for its convergence rate shown here. And as we can see, based on this recursion, the convergence of this algorithm is completely given by the values of our polynomial over the domain of the eigenspectrum of our objective matrix. So now that we know that the convergence rate of our optimization algorithm is completely dependent on this residual polynomial, it makes sense to ask the question, can we find a polynomial that satisfies the properties of the residual polynomial that has a better convergence rate? In other words, we want to ask if we can solve the problem here. Basically, we minimize over all degree t residual polynomials and try to find the polynomial that yields the smallest maximum value over our eigenspectrum. And we will call this the optimal residual polynomial because we can reverse engineer this polynomial if we solve for it to give us a better optimization method. And the reason that this minimization problem is not trivial is because of the residual polynomial property that our tth degree residual polynomial at 0 must be equal to 1. If the residual polynomial did not have to satisfy this property, this optimization problem here would be super simple because the best polynomial would just be 0 everywhere. So if we try and solve this problem, the interesting thing is that we actually know what the answer is from previous research and numerical analysis. The best possible polynomial is given by a shifted Chebyshev polynomial. And more specifically, it's given by the Chebyshev polynomial shown here, which is a quotient of 2 degree t Chebyshev polynomials. And here, the sigma function is basically just a transform function that shifts us from the domain of little l to big L, which makes sense for the optimization problem we're trying to solve, to a domain of -1 to 1, which makes sense for Chebyshev polynomials because this is the most common domain in which we study Chebyshev polynomials. And from numerical analysis, we know that this Chebyshev polynomial or shifted Chebyshev polynomial solves this minimization problem here. So now that we have this polynomial, we want to use it to reverse engineer an optimization method. And actually, if we plug in this expression for the Chebyshev polynomial, we can solve for all the coefficients c within our general gradient-based methodology and yield a new optimization method. And actually, what it yields is the Chebyshev iterative method. And if we take this optimization method and solve for its convergence rate, we get the linear convergence factor shown here, which if you compare this to what we got for gradient descent, it's exactly the same except all of the terms in the numerator and denominator have square roots, so it actually gives us a faster convergence rate than gradient descent. Extending our analysis of optimization methods for our quadratic objective, we can now look at gradient descent with momentum, which is given by the equation shown here. So the upper equation here is just a base case for if we don't have a previous iterate, but the main recursion for updates with momentum are given by the bottom equation here, where we can see that the momentum update actually has two terms. One of them is the difference of the current and previous iterate, which is scaled by our momentum parameter m, and then one of them is the gradient of our objective function, which is scaled by our learning rate and subtracted just as in normal gradient descent. And gradient descent with momentum has seen a huge resurgence in current research, mainly because stochastic versions of gradient descent with momentum have been very effective for deep learning. One interesting part of this recursion is that it actually is just a specialized case of our general gradient-based optimization method that we showed previously. And as a result, our proof for the residual polynomial convergence, which we express in the equation here, where our error at iteration t is given by a residual polynomial, still holds. So we know that our iterates still satisfy this equation here. As a result, we can then derive what the actual residual polynomial would be for our gradient descent with momentum update rule, and we get the residual polynomial shown here. And whereas before, for general gradient-based methods, the recurrence for our residual polynomial was very complicated and actually included a sum over all previous residual polynomials, the recurrence for gradient descent with momentum is comparably quite simple. And what this gives us is we can actually express our update rule and our residual polynomial as a very simple recurrence, which will be useful for analysis of this optimization method. Although we provided a pretty simple recursive definition for the residual polynomial associated with gradient descent with momentum in the previous slide, we can show that this residual polynomial for the momentum method can be reformulated as a combination of first and second kind Chebyshev polynomials. And this is given by the equation shown here. And to actually show that this expression is equivalent to our previous recursive definition of this residual polynomial, we could provide a formal proof using induction and the recursive definition of Chebyshev polynomials. I won't go in depth into this proof in this video, but if you're interested in more details, I would encourage you to check out the series of blog posts that this video is based upon, which are given in the description of the video. I believe the proof for this is actually given in the second of the 4 blog posts. So now that we have this expression for our residual polynomial, we can leverage this to derive a convergence rate. Again, we begin with the expression that shows that our error at the tth iteration is equal to a product of our residual polynomial with our error at initialization. And then by invoking norms on both sides and using Cauchy-Schwarz, we can arrive at a familiar expression that frames our convergence rate as the analysis of our residual polynomial. Then, if we plug in the definition of our residual polynomial shown here, we see that analyzing this polynomial or bounding the value of the polynomial over the eigenspectrum of our objective matrix simplifies to this expression on the right-hand side here. And what we see is actually the only unknown terms within this expression are the maximum values of a first kind Chebyshev polynomial and a second kind Chebyshev polynomial. So this term here is actually pretty easy to analyze as long as we can derive bounds in our Chebyshev polynomials. So in order to provide a convergence rate for gradient descent with momentum, we must bound the maximum value of our residual polynomial over the eigenspectrum of our objective matrix, which is given by this equation shown here. And if we look at this expression, the interesting thing is that we actually know all of the values within this expression aside from the maximum values of the first kind Chebyshev polynomial and the second kind Chebyshev polynomial. So these are our only unknowns within this equation. But luckily, we know from previous numerical analysis literature how we can derive bounds for these Chebyshev polynomials. We know very well how we can bound these maximum values of Chebyshev polynomials. And the simplest case that we can consider for this is the case in which the domain of the Chebyshev polynomials is between -1 and 1. As we mentioned when introducing the Chebyshev polynomials, this is the most common way to analyze Chebyshev polynomials. And this idea of the domain being between -1 and 1 translates to the input of these Chebyshev polynomials, sigma of lambda, having an absolute value less than or equal to 1. And if we use a distinction of cases and invoke the definition of sigma, we end up with this inequality here related to the setting of our momentum and learning rate parameters. And we refer to the momentum and learning rate parameters that actually satisfy this inequality as the robust region for gradient descent with momentum. And the interesting thing about this is we know if this inequality is satisfied, then the domain of the Chebyshev polynomials must be between -1 and 1, and therefore the values of the Chebyshev polynomials are bounded by plus or minus 1 for the first kind Chebyshev polynomial and plus or minus t plus 1 for the second kind Chebyshev polynomial. Therefore, we can plug these values in for our unknowns within this right-hand side of the inequality and derive a convergence rate for gradient descent with momentum. If we do this, the convergence rate that we actually get within the robust region is shown here. And one interesting thing that you'll notice about this is that our convergence rate in this case does not depend on the learning rate. Rather, it only depends on the momentum hyperparameter. And this curious property of our convergence rate for gradient descent with momentum within the robust region has actually been leveraged as inspiration for works like the yellowfin momentum tuner. If we go outside of the robust region, convergence rates can still be derived given certain settings. The robust region is not the only momentum and learning rate region that is convergent. And actually, the third blog post in the series of blog posts that this video is based upon goes into these different regions that we can have for convergence with gradient descent with momentum. So if you're interested in that, I would encourage you to read the third blog post. Interestingly, the convergent hyperparameters for gradient descent with momentum can be pretty easily mapped out as shown in this figure here, where the color represents the convergence rate, we have momentum hyperparameter on the x-axis, and the step size on the y-axis. And what we see here is that the convergence of gradient descent with momentum is separated into several regions based on the momentum and step size hyperparameters. Namely, there are three regions: the robust region, as we discussed before, something called the lazy region, and then the knife's edge, which are all dictated by different settings of our momentum and step size hyperparameters, which in turn correspond to different ranges in which we analyze our Chebyshev polynomials. As we mentioned before, however, the convergence rate within the robust region is only dependent on the momentum, which we can see here based on the change of the colors that the setting of the learning rate or the step size does not actually impact our convergence rate. This is not true in some of the other regions where we don't see a similar pattern. Additionally, we see that the best convergence rate given by the darkest colors in this heat map is achieved within the robust region. Namely, it's achieved by the smallest convergent momentum within the robust region, which occurs right here at the edge. And interestingly, if we analyze what values of momentum and step size lead to this best convergence rate, we get closed form expressions for something that we call Polyak momentum, which we will discuss next. Polyak momentum is a widely studied algorithm within acceleration literature. And it's just gradient descent with momentum, but with the following settings for the momentum and learning rate hyperparameters. Although Polyak momentum was not originally inspired by the use of Chebyshev polynomials, we see that our analysis of Chebyshev polynomials presented previously gives us a very different way of interpreting Polyak momentum. Namely, the settings of the hyperparameters within Polyak momentum correspond to minimizing the convergence rate of gradient descent with momentum within the robust region. And we can show this by invoking the convergence rate we derived for gradient descent with momentum within the robust region a few slides ago, as well as our maximum and minimum values of little l and big L, thus yielding the optimal settings for our hyperparameters, which correspond to the edge of our robust region. And if we then take these settings for our hyperparameters and plug them into our convergence rate that we derived previously, we see that the convergence rate achieved by Polyak momentum achieves a square root factor improvement in comparison to gradient descent. So before, for gradient descent, these square roots within the convergence rate were not there. It was just big L minus little l over big L plus little l. So we see that Chebyshev polynomials give us a way of interpreting Polyak momentum as a method that minimizes our convergence rate within the robust region, as well as gives us a very easy way to derive this convergence rate given our previous analysis. One final thing that I'd like to mention is how we can actually show an accelerated rate for gradient descent using Chebyshev polynomials without the use of a momentum term. So if we remember before, the way that we achieved an accelerated rate was by solving for the optimal residual polynomial, which then gave us an accelerated convergence rate that was better than normal gradient descent. and this led us to the Chebyshev iterative method associated with this optimal residual polynomial. But if we remove the momentum term within stuff like the Chebyshev iterative method, all that's at our disposal is setting the learning rate. So one thing we could do is use something called Young's method, which uses a curated learning rate schedule to achieve an accelerated rate without the use of any momentum term. So if you recall from previous slides, our convergence rate is derived from the residual polynomial. So if we want an accelerated rate similar to something like the Chebyshev iterative method, we need our residual polynomial associated with this method to match the optimal residual polynomial and therefore achieve the accelerated rate. And one interesting thing that we can notice here is that in order for the residual polynomial for our method to match the optimal residual polynomial, all we must guarantee is that they have the same roots. And this is sufficient because of the property that any residual polynomial, in order to be viable, must satisfy the property that the tth degree residual polynomial evaluated at 0 must be equal to 1. And this property of all residual polynomials allows us to say if the roots of our residual polynomial are the same as the optimal residual polynomial, then the polynomials must be the same. With this in mind, we can now consider the recursion for gradient descent without any momentum term, which is given by the equation shown here. And our goal is to solve for the optimal settings of all the learning rates such that we achieve an accelerated convergence rate. So each setting of our learning rate at time t can be different from time t minus 1 and so forth. We solve for all the learning rates from our first iteration to the last iteration. So if we invoke this recursive definition of gradient descent, as well as recall the fact that our error of our optimization method at time t is equal to a product of our residual polynomial and the error of our method at initialization, we can derive this formulation shown here. And the residual polynomial is pretty easy to see within this expression, so we rewrite it from a matrix polynomial to a scalar polynomial as shown here. And if we take a close look at this residual polynomial, what we notice is that the roots are very obvious. They're factored out into each of these terms. Furthermore, these roots are actually dependent on the setting of our learning rate. So because we can manipulate our learning rate, one thing that we can do is set our learning rate at each iteration such that the roots of this residual polynomial exactly match the roots of the optimal residual polynomial from the Chebyshev iterative method. And based on this property that we outlined previously, that two residual polynomials with the same roots must be the same, if we do this and set our learning rate such that we match the roots of the optimal residual polynomial, this residual polynomial is the optimal residual polynomial. And as a result, we achieve the accelerated convergence rate of the Chebyshev iterative method, which is all done by just selecting the proper learning rates for gradient descent. There's no momentum term. We just set learning rates to match the optimal residual polynomial, and we end up with an accelerated rate. Although we've studied relatively traditional applications within this video, such as Polyak momentum or the Chebyshev iterative method, the analysis of Chebyshev polynomials has been used in various applications in current machine learning research. For example, papers have been written in regard to Young's method and how it can be used to provide accelerated convergence rate using various learning rate schedules such as cyclical learning rates or arbitrarily permuted learning rates. Chebyshev polynomials have also been shown to prove acceleration for power iteration methods or even provide average case performance guarantees for gradient descent. And as mentioned previously, Chebyshev polynomials can be used to motivate things like the yellowfin momentum tuner. So Chebyshev polynomials are widely applicable in theoretical machine learning research, and their use cases are being constantly expanded to analyze new things like cyclical learning rates and so forth. If you're interested in learning more about this topic, I would encourage you to look at the blog posts that are linked in the description to this video, upon which this video was based. Thank you so much for your attention, and I really hope this video was helpful.